Hello again, and welcome to our lecture on the trigonometric form of a complex number. This lecture will combine a lot of different ideas. We'll bring in complex numbers, we'll bring in trigonometry, of course, as well as sort of the ideas of our previous lecture on vectors. This will be actually our final lecture on the series of lectures on trigonometry, and after this lecture we'll move on to a different subject. The ideas today will permit us to express a complex number very conveniently, and in particular permit us to find high powers or roots of numbers, and in particular complex numbers. And as I promised last time, at the end of the lecture, I'll show you a very beautiful formula involving e, pi, and the square root of -1. So let's remind ourselves a bit about that complex plane we looked at a long time ago in this pre-calculus course. Remember that we could represent a complex number, a plus bi, graphically as an ordered pair in the plane a comma b. The horizontal axis was often called the real axis, and the vertical axis the imaginary axis. Here are some complex numbers that we've plotted in the plane. You can see down in the third quadrant the complex number -2 minus I. The real part is -2, and the complex part, or the imaginary part, is minus I, and it's plotted as the ordered pair -2 minus 1. And then up in the second quadrant you see the number -1 plus 3I. And that's plotted as the ordered pair -1, 3. So there's a nice correspondence between complex numbers and ordered pairs in the complex plane. Okay, given this geometric interpretation, you can ask, how far is it from a complex number down to the origin? And that's called the absolute value of a complex number, its length. And the notation here is absolute value, the same notation as with real numbers, a plus bi with vertical bars. That's defined to be a squared plus b squared, all square rooted. That comes from, of course, the Pythagorean theorem. In particular, if your imaginary component b is 0, then of course you get the ordinary absolute value that we've learned to love in mathematics, absolute value of a, or if you want, the square root of a squared. Let's do a quick example to make sure we're comfortable with this idea of absolute value of a complex number. How about that number -1 plus 3i that we saw in the graph previously? How far is it to the origin, from that number to the origin? Or if you want, what's the absolute value of that complex number? Well, it would be -1 squared plus 3 squared, all square rooted, 1 plus 9, square root of 10. That's the distance from that complex number back to the origin. Now, the goal here in the next few minutes is to try to explain how to express a complex number in trigonometric form. This will be a nice interplay between complex numbers and trigonometry. So here's how it works. Consider the complex number a plus bi, which corresponds geometrically to the ordered pair a comma b. Now, if a comma b is in the plane, it has some components. A is the distance along the x-axis, b along the y-axis, and r is the distance to the origin, the absolute value of that number. So, in particular, r, the distance to the origin, or the absolute value, is often called the modulus, and theta will be the angle this complex number makes with the positive x-axis, just like in trigonometry. So, what is the trigonometric form of our complex number? Well, what's a? Remember the definition. Cosine theta is a over r. So a is r cosine theta. Just look at that triangle. Cosine theta is going to be a over r, and sine theta is b over r. In fact, that was the original definition of the trigonometric functions. R, of course, is the square root of a squared plus b squared. And if you take r sine theta divided by r cosine theta, that's b over a. The r's cancel and you're left with tangent theta. So what does all this say? Given this complex number, a plus bi, we can find out its angle theta by solving that equation, tangent theta equals b over a. And we can find the distance from the complex number to the origin by calculating the square root of a squared plus b squared. So, what's the complex form, or the trigonometric form, of our complex number? Well, let's call the complex number z. That's a very common letter, by the way, for complex numbers. Z is a plus bi, and that's r cosine theta plus r sine theta times I. And I here, of course, is the square root of -1. So that's r times the quantity, cosine theta plus I sine theta. That might look a lot like what we did last lecture with vectors. Now, of course, there's an I in this new equation. That's not the same I that we had in vectors. In vectors, I was the unit vector along the x-axis. This I is the square root of -1. But the similarities are pretty obvious here. We're expressing this complex number z in terms of two issues, two things. One is, how far is it from the origin? That was sort of like the magnitude of that vector. And also, what angle does it make with the positive x-axis? So in that sense, the expression is very similar to what we did with vectors. Again, in the literature, r is often called the modulus, and theta is the argument. These are terms to sort of, I like to tell students to keep the math club small, adding more words to mean things that you have to kind of memorize those terms. Let's not worry about that memorization, but just in case you're reading a textbook on this material, you'll see the words modulus and argument. They often call this the polar form of a complex number, and it's related to something called polar coordinates. You might have heard of polar coordinates. We'll be studying polar coordinates later on in this course. Also, that angle theta is normally taken to be between 0 and 2 pi, but remember the periodicity of the trigonometric functions. You can go outside that interval sometimes. All right, that's been a lot of talking. Let's do an example. Let's write the following complex number in trigonometric form. The number is z equals -2 minus 2 square roots of 3i. First of all, ask yourself, in what quadrant is this number lying? Right, it's in the third quadrant, isn't it? So that angle is going to be between 180 degrees and 270 degrees. So let's figure it out. First of all, what's the length of this complex number? Its modulus. Well, it's the absolute value of -2 minus 2 square roots of 3i. That's -2 squared plus the quantity -2 square roots of 3 all squared. And that's 4 plus 12 square rooted. That equals the square root of 16, or 4. Now, what about the angle? Well, remember, tangent theta is b over a. So that's -2 root 3 divided by -2, which is the square root of 3. Can you find an angle theta whose tangent is the square root of 3? But it also has to be in the third quadrant. So the angle would be in radians, 4 pi over 3. And finally, our trigonometric form is r times cosine theta plus I sine theta, 4 times cosine 4 pi over 3 plus I sine 4 pi over 3. Notice we've moved back to radian measure, and there's a reason for it coming up later on. Of course, you could also use degree measure here if you so choose. And I invite you to check this answer. Take that trigonometric form and convert it back to standard form. Let's look at another example. Let's look at now at a number that's already in trigonometric form and ask ourselves, what is the standard form of this complex number? And suppose the number is z equal square root of 8 times the quantity cosine minus pi over 3 plus I sine minus pi over 3. Notice how convenient this form is, by the way, before we do the arithmetic. I know the angle that this complex number makes with the positive x-axis, minus pi over 3. It's in the fourth quadrant. And I know how far from the origin this complex number is. It's square root of 8 units from the origin. All right, well, let's simplify. Square root of 8 can be written 2 times the square root of 2. And then cosine minus pi over 3 is a half. Sine of minus pi over 3 is minus square root of 3 over 2 times I. Multiply in that 2 square roots of 2, and you're left with square root of 2 minus square root of 6i. So here we've converted trigonometric form to standard form. Okay. You be the teacher for a moment. Student comes up and says, "Teacher, I got an answer for a trigonometric form of a complex number, and my friend got a different form for that complex number. Is that possible? Can a complex number have different trigonometric forms? Or is the trigonometric form unique?" What would you say to that student? Well, yeah, the trigonometric form is clearly not unique. Remember that periodicity of the trigonometric functions. In fact, here's something even more interesting. The number 0, the complex number 0, can be any angle it wants, can it? You could use any angle you wanted as long as you made the modulus r equal to 0. So this expression of a complex number in trigonometric form is clearly not unique. Okay, division and multiplication. These complex numbers can be multiplied and divided very conveniently. And let me just show you the formulas. They're beautiful formulas, and they're based on the summation formulas for the sine of a sum and the cosine of a sum. Here's how they go. Suppose Z1 is written in trigonometric form as R1 cosine theta 1 plus I sine theta 1, and the second complex number is R2 times cosine theta 2 plus I sine theta 2. Then their product, Z1 times Z2, you multiply the moduli, R1 times R2, times the quantity, cosine, and you add the angles. Wow, how simple. Cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And if you have a quotient of two complex numbers, all you have to do is divide R1 divided by R2, and then it's the cosine of the difference and the sine of the difference. So the plus sign changes to a minus sign. Let's do a quick example of this multiplication formula, and you'll see how nice it is. Suppose one complex number is minus 1 plus square root of 3i, and the other one is 4 square roots of 3 minus 4i. Now you could multiply these out as we've done earlier in the course, but let's use this new property for multiplying. Well, I'm going to first of all express both of them in complex form, in trigonometric form. And the first number is 2 times the quantity cosine 2 pi over 3 plus I sine 2 pi over 3. And the second one is 8 times the quantity cosine 11 pi over 6 plus I sine 11 pi over 6. That takes a little bit of work to get that trigonometric form, but I think you can do that. Let's multiply them out. This is a little bloody here, but I think we can get ourselves through it. The product would be, well, you multiply 2 times 8, and that'll give 16 out in the front. And then it's cosine of the sum of the angles plus I sine sum of the angles. And the sum of 2 pi over 3 plus 11 pi over 6 is 15 pi over 6, if you get a common denominator there. So it comes out to be 16 times the quantity cosine 15 pi over 6 plus I sine 15 pi over 6. But now wait, 15 pi over 6, that's coterminal with pi over 2. Think about it. 12 pi over 6 would be 2 pi, and then I'm left with 3 pi over 6, which is pi over 2. So 15 pi over 6 and pi over 2 are coterminal. So another way of writing this complex number, an equivalent way, is 16 times cosine pi over 2 plus I sine pi over 2. Well, what's cosine pi over 2? 0. What's sine pi over 2? 1. What's our final answer? 16 times I, or 16I. Whoa, kind of amazing, kind of simplified, didn't it? That's unusual, I think. Normally products don't simplify so nicely, but I thought it was kind of nice to have it come out to be a beautiful answer, 16I. And of course, you can check your answer by multiplying it in the normal way. By the way, dividing is very similar to multiplying, and you'll see an example in the workbook or an exercise in the workbook for you to try division. The good news is the complete solutions are also in the workbook if you have any trouble. All right. Well, this multiplication of complex numbers permits us to calculate powers of complex numbers. Here's how it goes. Let z equal an arbitrary complex number, r times cosine theta plus I sine theta. What would z squared be? Well, you'd multiply these two together. So the r's would be r squared, r times r is r squared, and the angles would be cosine theta plus theta. You add the angles, so it'd be cosine 2 theta plus I sine 2 theta. Okay, what would z cubed be? Well, you'd multiply that answer by another r times cosine theta plus I sine theta. So now it becomes r cubed. And what about the angles? You add 2 theta plus theta, 3 theta. Do you see a pattern? Z cubed is r cubed times the quantity cosine 3 theta plus I sine 3 theta. What if it were the fourth power? All the 3's change to 4's. Here's the general form. And it's a very famous theorem due to de Moivre. And we just about proved it, didn't we? Or at least we explained how it works. If your complex number is expressed in trigonometric form, r times the quantity cosine theta plus I sine theta, and n's a positive integer, then z to the n, taking that complex number to the nth power, is nothing more than r to the n times the quantity cosine n theta plus I sine n theta. That's pretty simple. That's an impressive formula. De Moivre, came up with a nice theorem here, I think. De Moivre, by the way, very famous mathematician, worked in all areas of mathematics, probability. He worked a lot with Fibonacci numbers, and we'll be looking at Fibonacci numbers later on in this course. So you have something to look forward to again. Let's do an example of de Moivre's theorem. Let's see how it works. It's kind of amazing, I think. Suppose you had to find the 12th power of minus 1 plus square root of 3i. So the complex number is minus 1 plus square root of 3 times I. And you want the 12th power. Well, of course, if you had a few free days, you could multiply that out in the usual way we did back in lecture 3. You could just multiply it, 2 of them, and then another one, and another one, and another one, and a few hours later you would have the answer. Let's see how this new theorem will give the answer really nicely. Okay. First of all, we have to express our number in trigonometric form. Minus 1 plus square root of 3i. That number has to be transformed to trigonometric form. Well, what's its length? What's its modulus? That'll be minus 1 squared plus square root of 3 squared, which is the square root of 4, also known as 2. How about the angle? Well, tangent theta is b over a, square root of 3 over minus 1, or minus the square root of 3. Well, where's this complex number located? Because it's minus 1 plus square root of 3i, it's in the second quadrant, isn't it? So the angle theta will be 2 pi over 3. Tangent of 2 pi over 3 equals minus square root of 3. That's one of our old trig skills coming back to haunt us today. All right, let's take this complex number now to the 12th power. All right, in trigonometric form, it's 2 times the quantity cosine 2 pi over 3 plus I sine 2 pi over 3, and that whole thing gets raised to the 12th power. What did de Moivre's theorem tell us to do? Well, the modulus part, the 2, just gets raised 2 to the 12th. That's easy. And what about the angle? Well, it's cosine 12 times the original angle. So it's 12 times 2 pi over 3 plus I sine 12 times 2 pi over 3. Pretty nice, isn't it? And that can be simplified to cosine 8 pi, 24 over 3 is 8, plus I sine 8 pi, and outside is 2 to the 12th, which is 4,096. Okay, we're almost done. What's cosine 8 pi? Oh, that's 1. What's sine of 8 pi? 0. Our final answer is 4,096. Wow. I wouldn't have expected that the 12th power of that complex number is so simple. In fact, it's a real number. It's 4,096. There's no complex part to that number. Kind of an amazing answer. And if you'd been doing it the old way, multiplying it out, you'd of course still be working on it, but you'll also get 4,096. All right, so we can take a complex number now, put it into trigonometric form, and raise it to a large power. Well, now we're going to kind of flip things around. Notice that 4,096 is the 12th. Let me say it a different way. The 12th root of 4,096 is the original complex number minus 1 plus square root of 3i. In other words, minus 1 plus the square root of 3i to the 12th power is 4,096. So the 12th root of 4,096 is the original complex number minus 1 plus square root of 3i. So in a sense, by raising something to a power, we've discovered one of the roots of it, one of the 12th roots of it. And you can twist around de Moivre's theorem and develop a formula for finding roots of complex numbers. And here's how it goes. This is how you find the nth roots of a complex number. It's a little complicated looking, but I'll do an example in a minute to show you how it works. It's kind of an amazing theorem. And it's based on de Moivre's theorem, but I won't show the full proof of it, of course. So here's how it works. Take a complex number, r times cosine theta plus I sine theta. The claim is that complex number z has precisely n distinct nth roots. It has 2 square roots. It has 3 cube roots, 4 fourth roots. This is in the complex number system, of course. And here's how you find them. Here's what the theorem says. To find those n distinct roots, they're of the following form. Well, the modulus is the real nth root of r. Remember, r is the modulus of the original number. So you take the nth root of r, the real nth root, and then you multiply it by the following expression. Cosine, and in the numerator, it's theta plus 2 pi k over n, and then plus I sine theta plus 2 pi k over n. Now that looks pretty complicated, but let me try to explain it. K takes on n different values, 0, 1, 2, blah, 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 out to n minus 1. So if you're finding fourth roots, k would be 0, 1, 2, 3. Fourth roots, n is 4, so you go out 0, 1, 2, 3. So there are really 4 values in this expression. When k is 0, you get a certain angle, theta plus 0 over n. Then you get theta plus 2 pi over n, theta plus 4 pi over n, etc. So as k varies from 0 out to n minus 1, you get a different angle each time in the formula, and each time you get a different nth root of your original complex number. All right, again, pretty complicated formula. Let's watch it in action. Let's find the 3 cube roots of 1. Now you might say to yourself, wait a minute, I know 1 is a cube root of 1 because 1 cubed is 1. But I claim there are 2 other cube roots of 1. Now, they're complex numbers. They aren't real numbers. There's 1 real cube root of 1, but there are 2 others hiding somewhere, and they're complex. Let's find them. It's kind of neat. All right. So first of all, we have to express 1 in trigonometric form. Well, that's not so hard. How far is 1 from the origin? 1 unit. What angle does it make? Angle of 0. 1 is on the x-axis, isn't it? It's on the real axis. So it's 1 times the quantity cosine 0 plus I sine 0. That's expressing the number 1 in trigonometric form. Okay. What are the 3 cube roots? Well, the nth root formula would be the nth root of r times cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n, k going from 0 to n minus 1. Here n is 3, so k goes 0, 1, 2. And out in front we have the cube root of 1. That's the real cube root of 1, so outside's just going to be 1. And then inside it's cosine of the angle. The angle was 0 plus 2 pi k over 3 plus I sine 0 plus 2 pi k over 3. Okay, so k takes on 3 different values each time it produces a cube root. Okay, how about if k is 0? Then if k is 0, the numerator is 0 plus 0, or 0, and you have cosine 0 over 3 plus I sine 0 over 3, sine of 0, 0, cosine 0, 1. The output is the root we knew about. We knew about 1. Now, here comes the fun part. Plug in k equals 1 into our formula. Watch what happens. The angle is theta plus 2 pi k, and k is 1, so it's 0 plus 2 pi over 3, and that is 2 pi over 3. So it's cosine 2 pi over 3 plus I sine 2 pi over 3. Oh boy, we have to know some trig now, don't we? What's the cosine of 2 pi over 3? Minus a half. The sine is square root of 3 over 2. So the second cube root of 1 is the complex number minus 1/2 plus square root of 3 over 2i. What's the third one? Well, now k is 2, so it's 0 plus 4 pi over 3, and that's cosine 4 pi over 3, which is also minus a half, but sine 4 pi over 3 is minus square root of 3 over 2. So the third cube root is minus 1/2 minus square root of 3 over 2i. Wow. A complicated theorem, but I hope you could sort of see how we did it. And we ended up with 3 cube roots. The one we knew about, 1, and then a couple of complex roots, minus 1/2 plus root 3 over 2i, and minus 1/2 minus root 3 over 2i. Now, I invite you to do a few things when you have a free moment. Each of those roots, cube it. I'll cube the first one for you. 1 cubed is 1. But if you cube the second one and the third one, you'll get 1 also. Those are cube roots of 1. They're pretty complicated cube roots. Anything else you noticed about them? They're conjugates, aren't they? They're complex conjugates of each other. That's kind of neat. In fact, there's even something more interesting to notice. Let's plot these 3 cube roots in the complex plane using our skills of plotting complex numbers as ordered pairs. Here's a picture of the 3 numbers. 1 is over there on the x-axis, and then we have a number in the second quadrant and its mirror image in the third quadrant, the complex conjugate of it. These 3 numbers are equally spaced on that circle. The cube roots are equally spaced on the circle. And there's a lot more that we haven't had a chance to touch on. If we were doing 4th roots of some number, they would also be equally spaced on a certain circle. It's a really beautiful mathematics here as you study the roots of complex numbers. Now, I promised you a famous formula before we finish this lecture. I'm not going to be able to derive this and prove it for you, but you have to trust me that if you take an advanced math class or a calculus class or a course in what we call differential equations, you'll see an equation that says that e to the a plus bi power equals e to the a times cosine b plus I sine b. Kind of looks like what we've been doing, doesn't it? But now it brings in the exponential function e. In this general equation, let a equal 0 and b equal pi. If you do that, you get e to the 0 times cosine pi plus I sine pi. Sine of pi is 0, cosine of pi is minus 1, and you're left with e to the I pi equals minus 1, or e to the I pi plus 1 equals 0. Talk about a spectacular formula. Here's a formula involving 5 of the most important numbers in mathematics, 0 and 1, which we're fairly comfortable with, pi, from geometry, e, the base of the natural logarithm, a number we discovered a few lectures ago, and I, the square root of minus 1. They're all meshed together, linked together in this beautiful, beautiful formula. I actually had a bumper sticker once on my car that said, "Mathematicians, we're number minus e to the I pi," which is equivalent to saying we're number 1. Okay, I think we can say we've finished for the time being our study of trigonometry and then vectors and then the trigonometric form of complex numbers. We're going to turn completely around now and begin a brand new topic. We'll be spending 4 lectures on systems of linear equations and matrices. So I look forward next time for the beginning lecture on solving linear equations. See you then.